Hello everyone, this is second class of the transient analysis, and in continuation of the first part, let's begin. So let us consider with an example the general procedure to find the total response of a network when equilibrium is disturbed. That means switch is closed or open. Most of you may be learning Laplace way, but very few people would have learned the time domain way. Sometimes it is very easy to go in the time domain way if they have asked the part by part, like natural response or forced response, and that will helpful. Also, sometimes it will be complicated using the Laplace transform for each elements, and then manipulate the your algebraic equations, then partial fraction it, then look up the table. So see at one go, I mean to say, I'll solve the differential equation how to write, and how to write the differential equation of the circuits. Then I will solve it very simple way. What are the laid down procedure? First write the character after the switching. What will be the circuit, whether series or parallel? Two options will be there. Then you write the characteristic equations, then solve the characteristic equation for the natural response. There you will have your arbitrary constant that need to be found later on. Then you find the before all this procedure, you need to find the initial conditions, like one initial conditions, variable of one initial condition, then its first derivative is required for the finding the arbitrary constant. Then we'll use the forced response, or you can say that is the particular integral. Then we'll add together, then find the arbitrary constant to get the result. Pay attention for this exemplified the questions. So here consider the circuits here. So you have a current source of 4 ampere connected with a switch. Okay, connected with a switch, and switch is closed at t equal to 0. You have IR, IL and IC. We have a 0.4 ohm resistors and 1/3 Henry inductors and 0.5 farad capacitors. Initial values of IL, VC are 2 ampere and 6 volt respectively. Before closing the switch, the initial voltage and current has been given. That is initial current through the inductors and initial voltage across the capacitors are 2 ampere and 6 volt respectively. The switch is closed at t equal to 0. Find the expression for current through the resistors 0.4 ohm for all time this. Okay. So first of all, I have told you that we need to find the initial currents. At t equal to 0, circuit becomes like this. Initial current through the inductor, that will be replaced by a current source of 2 ampere as indicated, as per the indicated directions. Then voltage across the capacitors is the 6 volt as shown in the figure. So you can easily find out the I0 IR. So with a very simple that is the manipulation or equation, because you see that this 6 volt voltage appears directly across regardless of the 4 amp or 2 amp, it appears directly across the 6 volt source. That means the initial voltage. So 6 upon 0.4, okay, 6 upon 0.4, which is 15 ampere. Okay, then IC 0 plus, so you can easily find out the IC 0 plus. So IC 0 plus will be the minus 13 ampere with a simple KCL. Then we need to find the DIR, that is the DIR upon DT. So we know that this is your IC is equal to C dVc upon dt. So you can find out the dVc upon dt 0 plus. So you got this result. Then we need to find that your, because our equation will involving the IR. Okay, so obviously we need to find the dir upon dt 0 plus. So we know these relations. You can see that IR is equal to VC, whatever the voltage VC, upon R, that is 0.4. So taking differentiation of both the side, you get dir 0 plus upon dt equal to 1 upon 0.4 is your 2.5, and dvc upon dt 0 plus. So by using the dvc upon dt 0 plus, you got the minus 65 ampere per second. We have got the initial conditions. Now we'll move to the second. After the switch is closed, the circuit, the natural response, when all the initial all the energy source are reduced to zero, when you reduce the zero, when your current source reduced to zero, so it will simply a open circuit, the circuit remains. The form of circuit is the parallel RLC circuit. So the characteristic equation, you know this, m square plus 1 upon RCM plus 1 upon LC equal to 0. Same characteristic equation prevails for the all the responses in this circuit. Similarly, I write the for series. For series circuit, the characteristic equation will be the S square 1 upon R by LS plus 1 upon LC equal to 0. Okay, this characteristic equation finding is very simple. Take the Laplace transform of both the side, VIS plus V0S, L will be simply 1 up LS, and C will be 1 upon CS. Put a potential division, V0S upon VIS, so it will be 1 upon CS upon R plus LS plus 1 upon CS. So taking all these things, 1 upon RCS plus LCS square plus 1. Okay, take LC common. So in the numerators it will be 1 upon LC. So when I take the LC common, so S square plus C common, so RYL S plus 1 upon LC. So this is the characteristic equation, simple. What about the left in the numerator denominators? This is for the series, and here the circuit configuration after the source is reduced to 0. So the characteristic is a parallel combination. So characteristic equation becomes this. So put the values, whatever the values are there. So m square 1 upon 0.4 into 0.5, 1 upon RC, then 1 upon LC, 1 upon 3 into 0.5. So ultimately m square plus 5m plus 6, which is m equal to minus 2, m equal to minus 3. So this is your complementary functions for the current. So C1 e raised to the power minus 2t plus C2 e to the power minus 3t. So this is the simple procedure. We do the analysis, or we found the solutions for the linear constant coefficient differential equation. Find the, so this is actually your natural response. Natural response, complementary functions is synonymous. Now one part is over. Then forced response. How to find the forced response? Forced response is the steady state response. So forced response will be the is the particular integral or steady state response after long time t tends to 0. So at steady state, equivalent circuit becomes when you allow the time for infinity. So what will be the response? So inductor will act as a short, capacitor will act as a open. So one is short, one is open. So obviously no current flows through the resistors because all the current will go through the shorted inductor. So steady state forced response is your 0. So now the total response is the natural response, that is complementary functions, and particular integral or forced response. So you have IR equal to C1 e raised to the power minus 2t plus C2 e raised to the power minus 3t. So because there are two constants, we need two initial conditions. So two arbitrary constants, so two initial condition. Another initial condition will be taking the first derivative of the IR. So very simple derivative, and we got the this. But using the initial conditions previously I have found, that is IR 0 plus at t equal to 0 plus, you have 15 ampere. So C1, when you put these values, so C1 plus C2 equal to 15. So we have also found before, that is dir upon dt 0 plus is minus 65. So minus cancel. So 2C1 plus 3C2 equal to 65. Then solving 5 and 6, very simple equations of two variable, linear equation of two variables. So you can easily find out that find out that is your C2 is equal to 35, and putting these values in the first equation. So C2, if C2 is 35, then C1 will be the minus 20. So ultimately the final equation will be the IRT equal to minus 20 e raised to the power minus 2t plus 35 e raised to the minus 3t for all time equal to 0. Too many steps involved to find the solution. In LTY we can find a single way go, but this is very simple one, that's why we could do it easily. But sometimes the you have underdamped systems, so that time you will have e raised to the power minus t minus at and cos bt and same way sin bt involves. So sometimes takes longer time, but it is a procedural is very simple, and I can say that making mistake, because we do mistake in the Laplace transform way while doing the algebraic manipulations, right? Otherwise that also take times, this also takes time, but Laplace way is easier to understand because here it involves too many steps. Find the initial condition, then differential equation, then characteristic equations, all these things. So for systems involving different differential equations of higher order, one has to use the concept of complementary functions or particular integral. So you got we have already done. So we are not interested in solving differential equations here, but illustrated how a simple problem takes number of steps and provide solution to provide the solution to responses. To reduce and simplify our efforts, we need to look for a smart way of conquering the problems. So that is how Laplace transform way comes in. So Laplace transform method is very powerful tool for analyzing transient circuit. It transforms an integral differential equations, ordinary linear constant, into a simple algebraic equations, which is easy to manipulate. This operational calculus was involved. This operational calculus was invented by the brilliant English engineer Oliver Heaviside. You have heard, you might have heard Heaviside expansions, that is partial fractions. So these are the things you can. What are the advantages of the Laplace transform way? You can go through Laplace transform for the LTI system. So this is the definitions. Let a simple let a signal or be x of t, taking the Laplace terms xt is defined as capital signal is the small x, capital X in bracket s 0 minus to infinity x of t e to the power minus at e to the power minus st dt. In order to xt be Laplace transformable, this condition has to be satisfied, that is absolutely integrable. The signal must be absolutely integrable. Why we take the 0 minus? This is the important point. 0 minus as the lower limit to include the origin and capture any discontinuity at x of xt at t equal to 0. Okay, that is del t ut, we need to capture it. Inverse Laplace transforms, this is a definition relevance, otherwise we don't use it in a direct instead we use the lookup table, Laplace transform pair lookup table, to get the time domain from the Laplace domain. So more detailed Laplace transform you will be studying in the signal and systems, but working knowledge of Laplace transform is required to handle the questions in the network theory. So Laplace transform of a e to the power minus at, a is a positive constant. So x of s 0 minus. So obviously this, and this is the integration, and this is a simple integration. Ultimately you will have e to the power minus a plus st limit 0 to infinity. Okay, that is clear. Minus a upon s plus 1. This one is clear. This is 1 is 0, e to the power 0 is 1. But how to deal with this term? You see, e to the power minus a plus s into infinity. Now I will split it. E to the power minus a plus del s equal to del plus j omega into infinity, right? So e to the power minus a plus delta into infinity and e to the power minus j omega infinity. Okay, so it is a to the power minus infinity. Okay, the infinity. So now the case is okay, so now case is this term can only be 0 if this is positive. Yes or no? If this total term is positive, that is a plus sigma should be, if it is greater than 0, then this term will be 0. I am not talking about this. This is the another way. This is always, if you take the magnitude, it will be always 1. So I am not interested in this term. This term will be 0 if, always it will be 0 if this condition is satisfied. So this condition is satisfied means sigma should be greater than minus a. What is sigma? Real of s should be greater than minus a. That we call the ROC, region of convergence. If you have small knowledge of complex plane, this is the real axis, this is the imaginary axis, and this is the, let's say, minus a. That means whatever the point here, real of s is always all the, because all the region here this condition is satisfied. So that means this is called the region of convergence of this Laplace transform. So we write in this way the transform pair. Okay, as we have, this is the point, why we will not find the ROC in network theory, because of this. As we have already assumed the network analysis is the causal, and this is the causal analysis, then we shall drop ROC in notation. ROC is to identify. You might have seen this e to the power okay, minus at ut e to the power minus at u of minus t minus. They both have Laplace transform of 1 upon s plus a. If you go by the control system, signal and systems, but they are differentiated by this for this real s is greater than minus a, for this real s is less than minus a. As we are considering only one-sided Laplace transform, that is causal analysis, that is for t equal to 0 greater than t equal to 0 case, all the case we are not interested t less than 0, because this signal is existing for t less than 0. So that's why we will always interested in this type of signal, and that's why we always invariably drop the ROC in the transform pair when we are dealing with the network theory. Then come to the singularity functions. Okay, single functions, we can say that is unit step. We can make more complicated signal using all these unit step functions, that is ut is equal to 1 for t greater or equal to 0, and you can say that t greater than 0. and for only t greater than 0, and for t less than 0 it is 0. There is a discontinuity here. From t0 0 plus 0 minus to 0 plus, there is a discontinuity. We are hardly bothered about what is the value at t equal to 0. Understand this. Unit impulse is defined as in infinity at t equal to 0 and 0 otherwise. So it is defined together. This definition is invalid if it is not mentioned. And minus infinity to infinity del t dt equal to 1. That is area under. It is so, though its magnitude or amplitude is infinity at equal to 0, but area is 1 only. Okay. Some properties. Okay. Some properties minus infinity to infinity x of t, when you multiply a signal xt and d with a delta function or impulse function and integrate minus infinity, it is simply gives the values of. This is called the sampling property of the impulse or delta functions. You will be more you will study more and more into depth in the signal and system. So we are just brushing up something so that you should not feel alienated when you go to the signal and system. If you have already studied, it's well and good. These are the enough for the analyzing the network problem. x1t equal to del 2t. What is the del 2t? So area, that means the strength is half. Then if del t by 2, strength is twice the original. So x3 del 1 minus 2t, so half. Whenever multiplied by 2, so the strength will be half, and you have a shifted by the occurring at the like this. The strength is your half occurring at half. Unit ramp tut. So ramp is simply x slope is 1, starting from 0, and the exponential you all know. See, very important here. A continuous functions multiplied by ut. What are the continuous functions? There is sine t, x, e to the power minus at, e to the power at, all these are continuous functions. So multiplied by ut, such as tut, e to the power minus ut, sine t, all are continuous at equal to 0. You cannot consider, because we are showing like this that it's starting from 0. Okay. So mere indicates that the multiplication of ut to a continuous function mere indicates that we are considering part of the functions for t greater or equal to 0 as a causal functions. Simple manipulation of the functions. Let the function be x of t. First we will discuss the shifting x t of t plus t0. When t0 is negative, it is called delayed. Okay. Delayed means when the signal is like this, delayed version will be the like this, and advanced version will be the like this. This is delayed and this is advanced. This is the original. So for t less than 0, it is a delayed version. T greater than 0, it is a advanced version. Example, you can check. So this is your ut. This is delayed by ut is delayed by 3 unit. So 1 t greater than 3, 0 t less than 3. Similarly, advanced version ut equal to 1 t greater than minus 3, 0 t less than minus 3. Folding or reflection. Folding is always, remember, whatever the signal be, the folding is always effected with respect to origin. The folding operation is always performed about the origin. That is the mirror. Whenever you stand in front of the mirror, your image is your folded versions. So let's the signal be like this: 0 and here 3. Okay, this is your 1. This is your x of t. The folded version will be the x of minus t. Put a mirror here. What you see? When I see the mirror, the respective distance will be like this. So I see the image like this, and obviously it will be at a minus 3. So this is your x of folded version. So always remember reflection about the origin. You can combine the folding and shifting operation. So you can do one by one, or you can do the first. For example, I want to do this. Okay, my xt is like this. Okay, this is a 0, 1. I need to find x of minus t plus 3. So simple operation is, first you do shifting. Okay, you do shifting, that is a advanced version, then fold minus t plus 3. Also you can do first fold it. Okay, let me fold first. Okay, then it's a positive, then advance it, that is move right to 3 unit. Right means delayed it, you can say. When a positive, move right. Okay, so let us do. So we have already x of t. So in this case x of 3t. For this case, then fold it, mirror image. This is your 3, 0. This way, first fold it. So x of minus t. Then move right by 3 unit, minus 3 plus t, 3 unit, move right 3 unit, 0, 3. Easy, whatever way. Then scaling with respect to the time axis, not amplitude. You remember that amplitude is not affected. Whatever the operation we are doing, amplitude is not affected. So when magnitude of alpha less than 1, it is linearly stretched. When magnitude of alpha greater than 1, linearly compressed. Is the best example here. 0 to 4 is the original signal. When alpha here x of 2t, where 2 is greater than 1, so linearly stretched, just linearly compressed by the 2. So just divide by 2 each point. Okay, in general case also you can do. Let's say 4, this is your 4, and this is your 2, and this is your x of t. So x of 2t will be the, just divide by 2 each point. So 1, 2, right? And x of let's say half t, just multiplied by 2, multiplied by 2, or you can say the same way, divide by 2, divide by the whatever here, divide by whatever here, alpha. Always you will be divided by whatever alpha. So alpha will be the, so this will be like this, 4 and 8, 4 and 8. So unilateral Fourier transform pairs, you need to always refer this constant V. Constant V. What is the V? V means V ut. Okay. All these are multiplied by ut, because I have mentioned here, don't confuse with the V is the starting from minus infinity to infinity. No, that's why I have to the unilateral Laplace transform. Always all the signal are multiplied by ut. So V equal to V upon S delta sigma, delta 1 ramp 1 upon S square, ramp to the power n or t to the power n un, n factorial, whatever there is a n, just bring it, and just s to the power n plus 1. If you want to remember, e to the power minus a t 1 upon s plus a, t e to the power minus a t, when I multiply t, 1 upon s plus a square. The general formula will see t to the power n e to the power minus a t, n factorial. See here, same thing. When I have t to the power n, n factorial, n factorial s to the power n plus 1. So in place of s plus 1, there is a property we'll discuss. Sin a t a upon s square plus a square, cos a t s upon s square plus a square, e to the power bt sin a t. Wherever s, put the b, just add the b wherever a. Similarly for cos also s plus b. Hyperbolic sin h alpha t, alpha upon s square minus alpha square, cos hyperbolic s upon s square minus alpha square. Remember this, whatever is the same as the cos or sine hyperbolic, only a sign, the instead of positive it is negative. So this property is used here when a signal has the x of t as the Laplace transform of capital X of s. When I multiplied by the e to the power minus a, it is called the frequency shifting. So whatever the e to the power minus a t, so it will be x plus a, and this is called the differentiation property, or in the Laplace domain. So t to the power n, whenever you have a signal xt which have a Laplace transform of x of s, when you multiply by the t to the power n minus 1 to the power n and nth derivative of the Laplace transform of the signal. So you can easily check. We have okay, we have, let's say, e to the power minus 2t, ut has the Laplace transform of s plus 2. What is the Laplace transform of t e to the power minus 2t ut? Okay, either way you can do. So first of all, do this way. So minus 1 to the power 1 and d upon ds upon s plus 2. So that will give you the minus 1 into minus s plus 2 square. So ultimately you get s plus 2 square. Also this is a reverse another property, that is that we have t has 1 upon s, 1 upon s square. T has the Laplace transform of t. When I say the t means t ut. Okay, I am considering all the transform inherently. I am considering all the transform as the unilateral Laplace transforms, that is all the signals are multiplied by the unit step functions. So when I have a t has 1 upon s square. With the frequency shifting property, we have wherever s, you put the add the 2, plus 2, make the plus 2. Scaling function has the Laplace transform of this 1 upon magnitude of a x s by a. Shifting property Laplace transform e to the power minus, this is very much used. All the properties are used. Then convolution, more detailed convolution will be discussed in the signal and system. X of t, ht, xs, hs. See the why it is 0 to 2. You might have studied minus infinity to infinity. Why 0 to? Because both the signals are 0 causal. You can say when both the signal are causal, then convolution sum will be this x of tau, h of t minus tau d tau. We'll study all about this property in detail in the signal system. This is a very important property. As a network is considered linear time invariant, when input x of t gives the output yt, if I shifted the input by t0, the output is exactly shifted, same time. Then periodic function for t greater than or equal to 0, half periodic, we can say, like see here. So obviously there will be a period. So how we calculated? 1 upon 1 minus e to the power minus ts, t is the time period of the signal, into 1 period, Laplace transform of 1 period, Laplace transform of 1 period, Laplace transform of 1 period upon 1 minus e to the power minus ts. T is the time period of the signal. Okay. All this literature you can, I don't think it is important. So you can also go through, if you wish, any good standard books give you the all this literature. Then Laplace transform for differentiation, provided the differentiation should not result into a impulse function or singularity functions. Then you can have sxs minus x of 0 minus. In general, we use the after, because it is considered for the t after the switching. So normally this form is used. Okay. Laplace differentiation of xt, first derivative of xt is xs minus x0 plus. If you want to second derivative of क्या हो रहा है यार? For second derivative, when you consider the second derivative dx square upon dt square, so simply extend it. You can, if you don't remember, then it can be extended. For example, let's say d upon dt dx upon dt, right? So for this we have as, right, lt of s, okay, s, then Laplace transform of dx upon dt minus d upon dt xt evaluated at 0 plus. Okay, this is not a bracket, this is the bracket s. Okay, now s Laplace transform of this dx upon dt, you know that minus this is minus x of 0 plus minus d upon dt x of 0 plus. So ultimately we have d square xt upon dt square has the Laplace transform of s square xs minus s x 0 plus minus d upon dt x 0 plus. You can extend same way, in this way. Only you need to remember this Laplace transform of first derivative, you can extend it. Then Laplace transform of integral, when integration is a 0 minus to t for continuous functions, we have xs upon s. When minus infinity to t, initial values or initial values has to be captured, and this is the initial value. What is this? xi at 0 minus or 0 plus, that is minus infinity to t x of t dt evaluated at t equal to 0 minus, as we are doing the first switching. So this is when xt equal to it. See here, xt can be it, so integration of I dt will be initial charge. Similarly with the vt, v dt will be initial flux at 0 minus. Or when the switch after the switch is closed, we see like this type, same, only difference is the 0 plus 0 minus, but 0 minus we least interested because we are considering the circuit at t 0 plus. Initial value and final value theorem, xt must be causal and xt and its derivatives, initial value and final value theorem. So initial value is always applicable to the causal systems, that means signal or systems activated at t equal to 0, and always 0 for t less than 0. So derivative must be Laplace xt and its derivative must be Laplace transformable. Remember that whenever you have a impulse, it does not come into this category, and should not be in higher order singularities in xt, and higher order singularity in xt means y, that is the del, that is differentiation of del t, all these things. Then initial value theorem said that is initial value of the signal is the limit s tends to 0 as xs. Similarly, final value you need to ensure that xss, that is s xs, must in the left half s plane. That is all the poles of s xs must be in the left half of s plane. So simply you can find out, because we are considering the physical circuits without any negative resistance, negative capacitance, negative inductance. So all the poles in the circuit elements when you transform into the Laplace transform way, you not find any pole in the right half s plane. Okay, so need not to worry about the right half s, that is the poles at the right half s plane as far as circuit theory is concerned. So need not to worry about this. So just apply this. But the question is how to identify the question coming from the network theory or signal and system. That is the biggest issue. So in general, you should remember. That's why I have mentioned all this. First you check S axis must not have any poles at the right half S plane. For example, just I am giving an example. Let's say this is your x of s, s minus 2, s plus 3. If I ask you what is the final values of this, so if you don't remember, only remember this formula, so obviously s a x s limit s tends to 0, so you have limit s tends to 0, s is cancelled, so 1 upon s minus 2 into s plus 3. Then you will say that 1 upon minus 2 into 1 upon 3, so minus 1 upon 6. So it is, but it is not correct. Why? Because this is not satisfying this now, because there is a pole at the right half of S plane. So in fact final value will be infinity, limitless. What do you mean by the infinity? Our circuit is finite, but our infinity means it will be limited, output will be limited, or you can say the device will be saturated. If there are the transistors, it will be saturated. If there are inductors, they will be saturated. Okay, if it's the mechanical system, there will be it will stuck at the there will be a mechanical stop will be there. Okay, it will be stuck there like that. So system is unstable, so final value cannot be calculated, or you can say it theoretically it may keep on increasing. Okay, so let us move to the waveform synthesis. That means how to write the different waveform mathematically. We'll go by the simple way, very simple. You try to concentrate here. We need to find a pulse equation for this pulse. So you can easily see that the pulse is like this. When a unit step functions, then we have cut with a scissor, we have cut at a equal to a. How to represent this? You see, first of all, you launch a step functions, then you launch a same value of step function but in opposite polarity at t equal to a. What happens when you add together? This will be there. Then ultimately this portion and this portion get cancelled, because here 1, here minus 1, all cancel. Ultimately we'll have how to write, that is, see here ut and 1 ut minus ut at a. So u of t minus a gives this pulse. Okay, now come to the triangular pulse. See, you know ramp, when there is a constant slope, so you launch the ramp, right? When I launch the ramp, but it goes to the 1 only, the slope is 1 upon a. Okay, the slope I have shown here 1 upon a, 1 a. So 1 upon a. But I don't record here. That means I have to subtract the same. When I launch here, what I'll do, I'll launch another pulse here, that is at the A, another ramp of the same slope but negative, that means opposite slope. Okay, that is this also 1 upon a but minus 1 upon a. So I got up to this, but I require this. Then again I will launch opposite slope, a ramp of opposite slope of value. See what is the values here? 1 upon a. So again that means twice of 1 upon a I have to launch. When I launch the twice of 1 upon a here, okay, the minus twice of 1 upon a here, so it get cancelled and it will come here, that is 1 upon a. Then again I have to launch 1 upon a at 2a. So finally I have 1 upon a RT. Okay, what is the RT? RT is your TUT. Okay, then I'll launch twice of 1 upon a to get this line, minus twice of 1 upon a r t minus a. Then I have to make it to 0. Then I will have a 1 upon a positive 1 upon slope in this direction here, so that this and this get cancelled. So r t minus 2a. Very simple. So this is the LT. Any slope, any type of functions you can manipulate here, like your simple functions we have studied, basic functions. Let's say 0 to 0 1 2. So I say I ask you find the signal in a mathematical form. What is the real? So you can see easily how you will represent this. Obviously starting from here means there will be a ut. So 2 ut. So I have a 2 ut, but immediately ut I keep on subtracting from this. Okay, so keep on subtracting for this. So what I'll do, I'll launch a ramp same way, at same point I'll launch a ramp of slope 2 upon a, that is I mean negative ramp. This is the negative slope. So minus 2 RT, and here I'll have a when it is come down, then I have to launch a positive slope here, this direction of same point at t equal to 1. So 2 r t minus 1. This way you can do. Same way you can try this way, 2 0 1. So find the Laplace transform of x of t. So all this manipulation you can practice. With practice only you can do much better. Then how can I write this? The pulse trend. So you can use this ut. Here I subtract u of minus u of t minus a. Then again I launch a 2a. u2 minus t is a. But here I will have a subtract it, make it 0. So keep on going. Then using the Laplace transform and properties, ut 1 upon s, here u of t minus a 1 upon s e to the power minus as, keep on going. So take common 1 upon s, 1 e to the power minus as plus e to the minus 2 is this. So 1 upon s into, see, this is the a, this is the, this relation, infinity GP series, geometric progressions, a upon 1, a upon 1 plus r. 1 minus r actually. Here a upon 1 minus r, na? 1 plus r square, right? Because here is the common factor, common ratio is the minus e to the power minus as, that's why it is coming positive. Another way, using the direct formula approach, using the direct formula approach, 1 upon 1 minus e to the power minus ts and ft of 1 period. Here the 1 period is the t equal to 2a, so, and the ft of 1 period is the 1 period, this one, that is ut minus u of t minus a. So ft of 1 period will be the 1 upon s into 1 minus e to the power minus as. So therefore put these values, so ft of 1 period upon 1 minus e to the power minus ts, so ultimately you will get this one. Okay, so next move to the this one, full wave rectified wave, full wave rectifier wave. So here you see, first this is the sine starting but ending is not there, so time period is like this here, 0 to 2 pi. So the xt is equal to, so first one you see here, I need to write for fast pulse, single pulse. What I will do, just forget the 1 2 3 like this. So 0, this is a pi, but this is like this. Okay, so period is 2 pi, so omega equal to 2 pi upon t, that is your period, that is 1. Okay, so I can write this pulse as like this. First let's write the first term, sin t. Okay, but sin t is the continuous, na, but I need to cancel all these things. What I will do here, I just add signal here, because it is keep on going, na, keep on going like this. So what will happen here, I'll add another here, shifted version of the sine. So all these terms are cancelled, I will have only one pulse. What is this shifted version? That means it's a 0 pi. If I shifted it by pi and add it, sine t minus pi, right? Write t minus pi and ut minus pi, because it is this is also sine t ut. So I have to add. So if sine t ut is this, so ut minus pi will be starting from here. So cancel, I got the pulse. Same way, second pulse you can do this. Second pulse is starting at the sine t minus pi ut minus pi, and then minus 2 t sine t 2 minus pi, t minus 2 pi and ut minus pi, and goes on like this. So ultimately sine t 2 sine t minus pi ut minus pi, so everything will be 2 and 2. So find the Laplace transform. So Laplace transform you can find this way or by the using the formula, that is 1 upon 1 minus e to the power minus ts. T here is the pi and time Laplace transform of 1 period. 1 period we have already seen here. So Laplace transform of 1 period will be the s square plus 1 plus e to the power minus pi s and s square plus 1. So putting these values, you will have this one. Oh, this one. Same way, you can any signal, you can easily find out the Laplace transform. Now come to the a beautiful questions. It has came in the GATE 2008. The circuit shown below is used to charge the capacitor C alternatively for two current sources. The switch S1 and S2 are mechanically coupled and connected as follows. For 2n t that is t greater or equal to 2n capital T, that is time period, and less than 2n plus 1 t, n0 1 2 3, s1 to p1, s2 to p2. This is s1 and this is the switch s2. s1 connected to p1 and s2 connected to p2, right? p2. That means for this time, for example, let's consider n equal to 0. For n0 means for t0 to t capital T, capacitors start charging through a constant current source of 1 ampere. You can see because capacitors start charging. Okay. Now for n0 we have considered for t to 2t, see 0 to t capacitor charge constant current source through a constant current source. Then for t to 2t capacitors discharge, क्योंकि this will be connected to Q2. Q2 means this will be connected to Q1 and this will be connected to Q2. So capacitor starts discharging through a constant current of 1 ampere. So what does it mean? That means your capacitor is connected through a current. This resistor is because the series resistor across a current source does not make any things in the circuit. So there is a current source in a single circuit. How I am representing? You see, this is your IT, this is your C. Okay, right? So, but I can write the IT in the mathematical form. For 0 to t capacitor charge through a 1 ampere current, this is your IT. Then from t to 2t capacitor discharge, that means a negative 1 ampere current. Then keep on going like this. So in effect, capacitor is connected with a symmetrical square wave of current source of amplitude 1. If you have identified this, then it is hardly takes another 30 seconds to write the whatever they have asked. Assume that capacitor has 0 initial charge, and given that Vt is a unit step function, Ut is a unit step functions, the voltage Vct across the capacitor is given by, and you know C is the 1 farad. So what is the relation for the voltage? V equal to 1 upon C integration of I dt, because step by step you have to do. So let us move. So for t0 to t, 1 upon C integration of 0 to t, this is the case, that is the slope 1, but it's at t, if the values become t, so t, then it do like this. So for this range Vct, initial voltage was the t, then 1 upon C from t to t. So this will be the t minus t, which is 2t minus t, 2t minus t. For t equal to t, this is a t. For t equal to 2t, it is 0. So now it is perfectly rectangular. This is the voltage across the capacitors. Now you just write your we have learned this way. So t ut minus 2t, then ut minus t this way, then t ut, then take the common 2. So minus 1 to infinity, you can see here it goes on to infinity, minus, because minus plus minus plus, so obviously there will be minus 1 to the power n, and all these value t to the power t into nt and u t minus nt. So you can match with the options. So let us discuss some of the basics things. Many people are on or off. So let us say we have a voltage source V and we have a capacitors here C1, C2. We need to find the V1 and V2. Okay, so Q will be same. I am going by the basic. Okay, and we know that C equal to Q by V. Let C1 V1 clear. C2 equal to Q2 V2, but series connection of the capacitors Q1 Q2 same, so Q upon V1 and Q upon V2, right? So divide both the equation, C1 upon C2 will be the V2 upon V1, add 1 both the side, so C1 plus C2 upon C2 equal to V1 plus V2 upon V1. Then what is this V1 plus V2? V, total voltage across the both the capacitors V1. So now V1 equal to C2 upon C1 plus C2 into V. Similarly, V2 will be the C1 upon C1 plus C2 into V. Okay. Similarly, you can do it yourself. Okay. Like I can say the current source. Let's say current I through the inductor L1, L2. You need to find I2, I1. Try it yourself. Same principle. Here the capacitor, there will be the that is the inductors L di upon dt, or you can say the relation psi flux linkage psi equal to, just a indication, flux linkage equal to Li. Now you can easily do. Okay, see you in the next part. Another important part will be there, maybe another two parts of the transient analysis. There will extensively, that almost exclusively use the Laplace transform. That is, we will find the Laplace transform of initial voltage, initial current through the inductor, initial voltage of the capacitors, how to solve the differential, how to convert the differential equation to the into the Laplace transform way, and how in the circuit itself how can we find the convert into the Laplace transform way, how to find the algebraic equation, then manipulate it, then partial fraction it, then we'll look up the transform pair table, and then find the ultimately your time response. All these things will be discussed maybe one part or two part in the next class. Thank you everyone for watching this video. Please subscribe, then we'll see the I'll upload more and more video. Okay, see you in the next class.